Welcome to the NMN video tutorials on CSP technologies. Block 6, Unit 1. Introduction to Thermal Performance Testing and Mobile Measurement Laboratory. My name is Nicole Janot, and I have been working on CSP technologies at DLR for more than 6 years. My main fields of work are parabolic trough and component performance testing, as well as test evaluation and performance simulation. At the beginning of this introductory unit on thermal performance testing of parabolic trough systems and components, the general motivation will be given. Then, the basic approach towards performance testing as well as important measurements are introduced. Further on, different scale test facilities for thermal performance testing are presented and their characteristic strengths and weaknesses considered. The mobile field laboratory is introduced as an alternative, installation-independent approach towards performance testing. The unit closes with a summary of the main findings. Generally, the term collector performance testing encompasses all efforts to characterize a collector performance by means of testing. In the context of the following units, we shall only refer to performance in terms of thermal performance, however. In other words, performance that is measured as a function of the thermal collector output. There are a number of reasons one might be interested in thermal collector performance. First of all, thermal performance is a key figure in verifying collector characteristics anticipated from design, components, and simulation. Thus, it is essential to support and verify efforts in research and development processes. Furthermore, as the number of collector designs and component manufacturers increases, the need for comparative studies and testing rises. One of the central questions in this context is how differences in design and optical properties affect the overall performance of a system. This is closely linked to the aspect of component and collector qualification that aim at demonstrating performance under representative boundary conditions. Besides, performance test results are the basis for most technical and economical feasibility studies, the plant layout and prediction of power plants' performances. And last but not least, as a criterion quantifying the overall performance of a solar field, performance testing typically is an important part in the process of commissioning and acceptance of solar fields. The collector development cycle of a utility-sized parabolic trough collector typically consists of 3 stages. Based on first ideas, a general concept is developed, the components are sized, and a prototype collector is erected. This prototype is then submitted to thorough testing of mechanical, optical, and thermal performance. Mechanical testing encompasses a characterization of general torsion stiffness, torsion effects due to poor balancing, tracking precision, and hysteresis due to bearing friction. Optical testing aims at determining the quality of a collector's geometrical features in terms of intercept factor. Thermal testing for overall performance of a system is typically last in the testing chain and also comprises the characteristics of the receivers. While mechanical and optical tests are conceived to identify actual performance problems and localize their sources, thermal testing is more of a final check. All test results obtained are the basis for the revision of the design and implemented in a second prototype or directly in the first mini-series of a collector. Collectors from the first mini-series are then used to install the test loop. The dimensions of this installation often reach those of a regular power plant loop. Test loops can be installed at the sites of test centers or existing parabolic trough power plants. Thermal, optical, and mechanical testing at the test loop serves for a first assessment of the series production and assembly procedures. Furthermore, it proves the functionality and performance under actual operation conditions. Again, test results at this stage generally trigger collector enhancements. Finally, the new collector design is used in commercial application for the first time. An overall performance test of the solar field, a so-called acceptance test, during its commissioning and acceptance phase, constitutes a large-scale performance test. As illustrated in the diagram, mechanical, optical, and thermal performance testing matters at every stage of collector development. Especially the overall system performance converting solar irradiance to useful thermal heat serves as a criteria for assessing the effective quality of an assembled parabolic trough collector system. So what are we looking for in performance testing? Generally, performance testing is intended to fully characterize the thermal and optical behavior of a system. In order to do so, a number of characteristics are particularly relevant. The peak optical efficiency for clean collectors and normal incidence of the solar irradiation summarizes the capacity of the system to concentrate the incident solar irradiance onto the receiver and convert it into heat. The incident angle modifier characterizes optical losses of the system relative to its peak optical efficiency. The incident angle modifier is a function of the angle of incidence. These losses generally increase with increasing angles of incidence. The thermal efficiency is another important quantity. It expresses how much of the heat initially absorbed is made available as useful heat of the system. As the heat loss to the surroundings generally increases with increasing system temperature and hence temperature difference to the surroundings, thermal efficiency decreases with increasing system temperature. The response of parabolic trough collector systems and associated field piping to changes in temperature and irradiance, thus the transients of the system, determine the operational characteristics of parabolic trough solar fields. And last but not least, the uncertainty of the above characteristics or parameters is decisive for the interpretation and significance of performance tests. The lower the uncertainty, the more meaningful the results are for the system comparison and yield prediction. What is an adequate measure to quantify the thermal performance of a parabolic trough collector, loop, or field? As the heat transfer fluid passes through the collectors, it gradually heats up. The overall thermal performance of a parabolic trough system is thus expressed as the gain in enthalpy of the heat transfer fluid between the system inlet and outlet. To this end, the mass flow rate of the HTF, its temperature at the system inlet and outlet have to be measured. The specific heat capacity of the HTF can be determined in laboratory tests. The useful thermal power of the solar system determines the power available to a steam cycle or other subsequent uses. In order to relate this useful thermal power to the available solar power and prevailing ambient conditions, these are recorded during performance testing as well. Finally, the system performance is expressed as efficiency or specific useful heat rate or power for a set of meteorological boundary conditions. In order to draw conclusions on system performance under actual solar field operation conditions, a set of testing requirements is to be fulfilled. It goes without saying that, among others, actual operation conditions of the latter application are to be reproduced during testing. This mainly applies to fluid temperatures, levels of irradiance, flow rates, and angles of incidence. Furthermore, in order to facilitate later parameter identification, specific constellations of operation conditions are needed. As mentioned before, small measurement uncertainty is essential to generate meaningful test results. And in the case of system assessment for certification purposes or in the context of acceptance testing, the independence of measurement matters. This set of testing requirements is to be balanced with the general testing restrictions of limited time, effort, and resources. Therefore, test facilities always represent a trade-off between desirable test conditions and required human and financial resources, as will be shown in a minute. Such test facilities are typically used for prototype and component testing and characterization, as well as comparative studies. In order to provide close monitoring, maintenance, and qualified test staff, they are situated at the sites of test centers like the German Aerospace Center, Plataforma Solar de Almería, or the National Renewable Energy Laboratories. In terms of testing conditions, like the kind of HTF used, its flow rate, maximum dimensions of a unit under testing, or angles of incidence, their design always constitutes a compromise between desirable test conditions and investment in the test infrastructure. As a consequence, test conditions are limited in one way or the other depending on the main focus of the test facility. Furthermore, test facilities provide the required data acquisition infrastructure. This includes built-in sensors and data logging. The downside is that tests at test facilities usually require a long-term planning in order to install the components to be tested. As the number of component manufacturers and thus potential clients increases, the limited availability of testing times can represent a bottleneck in system or component development. In the following, a selection of test facilities for utility-scale parabolic trough collectors will be presented by Test Laboratory. DLR's rotating test facility, called CONTAS, is designed for two-axis tracking of parabolic trough collector modules up to a maximum length of 20 meters. The two-axis tracking system allows to set the incident angle independent of the season and time of day. For reasons of operational ease and safety, the system uses Siltherm 800 as a heat transfer fluid, not VP1, as current parabolic trough plants do. The balance of plant is designed for cold and hot tests. It provides very stable fluid inlet conditions and dissipates the useful heat collected. Furthermore, the facility is equipped with high-precision sensors and data acquisition. A similar two-axis tracking test facility is the Azimuth Tracking platform provided by Sandia. It also operates with thermal oil and can accommodate collector modules of up to 12 meters length. The balance of plant can be used for cold and hot tests. The third two-axis tracking platform available is the large payload solar tracker operated by NREL. It is designed for cold tests, hence determining incidence angle modifiers, and tracks units up to 4,000 kilograms with an accuracy of ±1 millirad. The heat transfer fluid used is a mixture of water and glycol. On the scale of collector loops, CMET provides various test facilities at Plataforma Solar de Almería. There's the 700-meter-long DIS loop in north-south orientation. It is operated with water and designed to test components as well as control strategies for direct solar steam generation. Next to the DIS loop, a 100-meter linear Fresnel collector was erected. The systems are interconnected so that the Fresnel collector can be tested in preheating, evaporation, and superheating mode in spite of its limited size. There's also a large testing unit operated with Siltherm 800 that consists of 3 parallel rows of collectors in east-west orientation. This orientation is very favorable for testing as it ensures perpendicular irradiance at solar noon on any day of the year. One of the rows of these facilities is equipped with part of a Eurotrough collector. Field tests are carried out at the sites of existing or new power plants as depicted in the photographs of the SEX solar electricity generating system plants and the Puerto Herrado Fresnel direct steam generation plant. Many existing designs of parabolic trough collectors have been tested in test loops, for example at the site of 6.5, the solar field depicted in the northeast of the aerial view. There, the modified test loops can even be identified on the picture due to the resulting irregularities of the field. In terms of temperature levels and angles of incidence, the boundary conditions of field tests are defined by the plant setup, like orientation and HTF, and operation. There are 2 approaches towards the acquisition of power plant data, using either built-in regular sensors or extra mobile measurement equipment. The different approaches will be discussed in more detail in the following slides. Field tests typically aim at the verification or enhancement of the performance of an existing solar field. When choosing between options of sensing and data acquisition for field performance testing, there are 2 main approaches: Clamp-on sensors, meaning sensors mounting externally to the piping, and built-in sensors, the ones that are regularly installed in parabolic trough solar fields. In terms of the main selection criteria, the approaches differ characteristically as shown in the table. Generally, measuring fluid-bound properties is easier using built-in sensors as they are in direct contact with the medium. They have the potential to measure with higher precision and accuracy than clamp-on sensors, provided correct calibration, characterization, and mounting. However, being part of the HTF system, built-in sensors are difficult to trace and recalibrate. Consequently, these procedures are typically not very frequently carried out. Therefore, built-in sensors may not perform to their full potential precision and accuracy and are to be reviewed individually. Changing built-in sensors requires an interruption of the plant operation and is associated with considerable mounting effort as well as leakage hazard. Therefore, their flexibility is rather poor. The effort required for high-quality measurements using built-in sensors is relatively high and only justified for long-term measurements. Clamp-on sensors, in contrast, are only installed during the period of testing and can be calibrated before and afterwards. As they do not interfere with the HTF system, there is no leakage hazard and no plant interruption is required for mounting them. The overall mounting effort is low, and thus clamp-on sensors are particularly interesting for short to medium time measurements. Especially when an independent performance assessment is required, clamp-on measurements benefit from their standalone sensing and data acquisition concept. For this application, a mobile measurement laboratory has been conceived. The concept of the mobile measurement laboratory is based on 5 principles. The non-invasiveness, meaning that sensors have no direct contact with the HTF. This implies that the system does not have to be opened for their installation, so there's no leakage hazard. No constructional changes are required either, as sensor designs are applicable to standard HTF piping. The robustness. Sensors and data logging devices must be fail-safe and the least unsusceptible to handling errors as possible. Furthermore, they should be weatherproof. The flexibility. Sensors and loggers should be applicable to different size systems and pipes as well as common heat transfer fluid media. The compactness. The compactness is an important factor in terms of portability of the mobile field laboratory. All components can be secured in standard cases. And the ease of use. The ease of use during testing can save time and enhance measurement data quality by easy mounting and dismounting, as well as options to monitor and check data in parallel to recording measurements. As for the mobile field laboratory, the choice of the measurement equipment according to the previously discussed criteria has led to the following components. PT100 temperature sensors with shields and heat-conductive paste to be enveloped in mineral wool and covered with aluminum foil and fixed with aluminum tape. A clamp-on inclinometer, a clamp-on ultrasonic flow meter, a mobile high-precision irradiance station, and sensors for wind and ambient temperature, a portable reflectometer, and a set of mobile data loggers. The sensors and their measurement principles will be discussed in more detail in the units 3 and 5 of this block. So this unit can be summarized as follows. The relevance of performance testing as the ultimate method for overall performance assessment of a system has been discussed for different levels of collector development and implementation. In this context, the relevant testing environments have been introduced and compared, illustrating the respective advantages and disadvantages of testing at a test facility and in the field. Furthermore, the basic philosophy of the mobile field laboratory for independent and temporary measurements has been introduced. This includes a presentation of clamp-on equipment as well as mobile data logging. Now we come to the end of this introductory lecture on thermal performance testing and the mobile measurement laboratory. Thank you for your attention.